Welcome to the third video from the software engineering series. It talks about the essence of requirements engineering and why it is important even in agile methods. Significant number of innovations in all areas of software industry tend to follow the Gartner hype cycle. Now, this cycle is not scientifically proven, but there are lots of evidences that it is true in general. Agile methods have succumbed to this cycle too. The problem is not by itself with the many valuable principles and practices advocated by the Agile Manifesto, but with misunderstandings, misapplications, and aggressive marketing approaches of sticking that term, in this case agile, to everything for the purpose of increasing the likelihood to sell stuff. In other words, people have been doing agile in wrong way for a very long time. This video will showcase the importance of adequate requirements engineering even in the agile context. It will explain the differences between user and system spaces, and it will highlight why there is a need for some upfront design work to cross the gap between these two worlds. The table of contents is as follows. First, we will introduce our problem description to have something to work with. Then you will see how to transition from a user to a system space, as well as learn about the fundamentals of reuse-based software engineering. You will also learn about one algorithm and method to check whether a graph is bipartite. At the end, we will reflect on various requirements models and processes. Here is the problem description. We will solve two problems from LeetCode using Java, possible bipartition and is graph bipartite. More specifically, we will analyze if there is an association between these two problems, and if yes, then how to leverage it. We want to simulate both the creation of a new reusable asset as well as reusing an existing one. Here is the possible bipartition problem. I am showing here only the first paragraph, which describes the business case. Many times it is called a business use case. And it says we want to split a group of n people, labeled from 1 to n, into two groups of any size. This means that we don't need to care about how big those groups are going to be, only that we are properly assigned people to those groups. Each person may dislike some other people and they should not go into the same group. So essentially, this is the only criteria by which we are going to group people. The business use case is describing what the system needs to accomplish to satisfy the user, and it takes into account viewpoints of many different stakeholders. I am using the term system in a much wider sense here, not necessarily meaning only a software system. The extent of automation and coverage of a business process achieved through a usage of a software product is what defines the scope of a product. Scope of a product. Proper scoping is quintessential for the success of your project. Many agile projects fail exactly due to ill-specified scope. Suppose that in our case we have scoped the software product as follows. We have divided our features into two groups, in scope and out of scope. Now, these features, once again, are associated with that system in a wider sense, and only those which are marked as in scope are going to be covered through a software product. Massage input means that we will do any necessary input acquisition and pre-processing of that input for being able to process it later. Check if bipartition is possible is going to be the main feature of our software product, and also we will give a chance for a user to retrieve the groups. Now, out-of-scope features are those that are not going to be covered at this moment via a software product. It doesn't mean that in the future it won't be covered, just that now these useful things are going to be accomplished in other ways. For example, building a user profile from social media information is definitely a very interesting artificial intelligence task, and it could be covered in the future even with software. Determining dislikes based upon these profiles is again a very interesting feature and could be automated in the future. Balancing groups means shuffling people around who can be shuffled, and to have groups of nearly equal sizes is something that obviously is also possible to be done through a software. Now that we have established a clear scope, we can proceed further to specify the product use cases. The product use cases still use business terminology and are talking about user goals, but those goals are now specifically associated with the software product. At this point, you are ready to produce the matching use case diagram, which is shown on the right. It visually depicts the in-scope features of your product, and notice that the scope is delineated by this rectangle. By the way, this diagram was generated by the PlantUML tool, and you may find the source code for this image in the GitHub repository of this YouTube channel. Let's look at the possible bipartition problem in full. Previously, we have been focused on this upper part that we denoted as business use case. This lower part is what we mentioned to be a product use case. Now, the product use case is talking in terms of specific features of a product and how those features are covering the business use case. Given the integer n and the array of dislikes, where dislikes of I is equal to the pair of AI BI indices, indicates that the person labeled AI does not like the person labeled BI. And we should return true if it is possible to split everyone into two groups in this way. We have three examples here. For example, this one is saying that we have four people, and the dislikes array says that person number one cannot be put into the same group with two, one cannot be put into the same group with three, and two and four must be put into separate groups. And in this case, we can partition people into two groups. For example, group one can be 1 and 4, and group 2 can be 2 and 3. Example 2 and example 3 are cases where such a bipartition is not possible. We also have constraints here. For example, the number of people can be between 1 and 2,000. The number of dislikes can be 0 up to 10,000, which means that we can have at most 10,000 of these pairs. And we are also given that all the pairs of dislikes are unique. Now, a constraint is a specific type of requirement, and constraints are very important because based on them we can reason about how performant our software solution needs to be. At this point, we must figure out how to embark on implementing our product. We can take two routes: specify selection criteria for reuse, or specify detailed system requirements for a reusable artifact. Both options demand design work. For example, we can first try to find a reusable asset, and if we cannot find such, then we might want to implement it from scratch. All of this is the basis of reuse-based software engineering. Now, let me emphasize that there are myriad of reasons why a particular company would select one route over the other. However, such an analysis is out of scope of this video. Our aim here is just to simulate both approaches. So we will proceed with crafting a shared service, in other words, demonstrate the lower route first, and later illuminate the upper direction too. Here is the isGraph bipartite LeetCode problem. Now, the reason that we need to invest design work before writing a system specification for a reusable artifact is because we need to know how to implement such a service. First of all, we need to figure out what data structure and algorithm to use. And also, what is even more important, that we want to craft a reusable API, and of course an associated implementation that's not tied to a particular business use case. In other words, we want now to create such a service that can be easily applied to solve many similar problems. Apparently, this specification is quite different from the previous one, and it talks in terms of graphs. Now, how we came to this point that we are now having this sort of a specification? Well, that's the outcome of our design work. It is straightforward to establish a one-to-one mapping between our initial problem and this graph problem. If we represent people as nodes in a graph and represent the dislikes relationship as edges between those nodes, then it's obvious that a dislikes relationship, dislikes of I, which was represented as a pair of indices, where these are identifiers of people, we can see that if two persons AI and BI dislikes each other, then we would create a link between them. Let's look at example 1 here. We have 4 nodes from 0 to 3, and these are defining the edges. And by the way, defining a graph in this manner to list the adjacent nodes is called adjacency list. And if we represent this as a two-dimensional array, as in this problem, then the first dimension is high-level pointers to subordinate arrays, which are arrays of neighboring nodes. In our case, for node 0, 1, 2, and 3 are its neighbors. For node 1, it's 0 and 2. For 2, it's 0, 1, and 3. And for the last one is 0, 2. And this case is saying that the output is false because there is no way to partition the nodes into two independent sets such that every edge connects a node in one and a node in the other. There are different approaches how we can implement a bipartitioner. For example, we can use depth-first search, breadth-first search, we can use a union-find data structure, but for simplicity reasons I am going to use here a depth-first search, which is a basic graph traversal algorithm. Since we are simulating here a shared service, let it call it as a graph, and the fact that it's represented as a class is just that it's now we are simulating the whole thing. And suppose this is a microservice. This is a very simple class, and I have attached here a Java documentation to simulate also an important aspect of creating a shared service, and that's documentation. Now, after creating an instance of this class, the client would call this public bipartition method. And the way how it works is very straightforward. And let me first show you the usage scenario here. This class solution is part of a LeetCode template, and this is the method that is provided by LeetCode, and we cannot change the signature of this method. Only what I have changed is the name of this argument here to better reflect what we are accepting. And this is how this class would be used to return a boolean whether a graph is bipartite or not. Let's see how this works. Here is the graph that we will use as an example to trace the execution of the code. We first create here a groups array of n with n elements, and initially these groups is filled with nulls. So we have groups as an array of null values. And we will have 4 of them for each node, and let me denote null here as in this manner. Inside this main loop, we iterate over each node of a graph from node 0 up to n-1. And if the node hasn't been visited yet, which means that its assignment is still null, then we are calling the private method bpartition and testing whether it's false. And if it's false, then it means that we cannot partition a graph and immediately return null. And we are passing the current node, we are passing the initial assignment to that node, which we always start as group A, and we are passing this groups array. Inside this bpartition recursive function, we are doing this depth first search starting from this node that's been passed here. Suppose that it's node 0. Now what happens is that since the node is still unassigned, we assign it to the assignment that was here passed as group A. So let me denote it is in other color. So we assign this to A, and also we obviously write a value here that it's now assigned to A. And what we are doing here, since this node is assigned now to A, that means that all neighbors must be assigned to a separate group, because this edge means that the neighbors cannot be part of the same group. So that's the reason why we are calculating here what is the opposite group. In this case, it would be B. Next, we traverse the neighbors of our node and recursively call this bpartition function, each time passing the demanded group for that neighbor. And since this happens recursively, all these recursive calls are better or easier to explain just by tracing what happens visually on this graph. So let's now do that. And since we are demanding node 1 to be assigned to group B, when we recursively call this bpartition function, that's exactly what's going to happen, so that node 1 is going to be assigned to group B because it's currently unassigned. So this will become B here. And now node 1 is going to traverse its neighbors. And suppose that it first traverses or tries to traverse now in opposite direction and recursively call node 0. But this time, since node 1 is assigned to group B, the opposite variable would be here assigned to group A, and when node 1 recursively calls the bpartition function passing 0, notice that this if statement will be false because 0 is already assigned to group A, and we are not allowing reassignment. And what happens here is this check whether the required group is the same as what's already been stored here. And in our case, since 1 is demanding 0 to be in group A and 0 is already in group A, this will return true. So this will be okay. Next, node 1 will call recursively for node 2, passing group A to be a required one. And since node A is still unassigned, it will be assigned to group A. Suppose that the node 2 is going to call bpartition for node 0. And this is where interesting thing will happen. Namely, since node 2 is already assigned to group A, it will require node 0 to assign to be assigned to group B. But since node 0 is already assigned to group A, this check will here fail and return false. Once it happens, all the recursive calls will unfold and return false from each nested level, which means that this bipartition will return false to this top level loop here. And as a result, null will be returned. And this is the case where bipartitioning is not possible. Suppose that we don't have this edge. In this case, bipartitioning would be possible because when node 2 would call bipartition for node 1, it will receive true. And for node 3, which is still unassigned, it will be assigned to group B. And when node 3 is going to call bipartition for node 0 and node 2, both will return true. And at this moment, since we are here at the level of recursion for node 3, we have finished executing this if block, and this check will trivially return true for node 3 because what we are checking here whether this assignment was successful, which is obviously the case. And once every node reaches this statement, this means that it will exit the recursive call, and this unfolding will happen until we reach the top level node, and in our case this is node 0. And node 0 will return back true, and the bipartition function will return back groups. Now, the reason that we need to iterate over all of these nodes is when we have a disconnected graph. Suppose that we have the following two subgraph: 0, 1, 2, and 3, and down here we have 4, 5, 6. And when we first finish processing this subgraph here, only nodes 0, 1, 2, and 3 are going to be assigned to proper groups. And in order to process also this subgraph, we need to find the entry point, either 6, 4, or 5. Once we start processing this subgraph from any of these entry points, all of them are going to be assigned to proper groups. So that's the reason why we need to go over every single node here. Notice also that if we start from, let's say, node 0 from here, and assign node 1, 2, and 3 to proper groups, when we iterate over again node 1, 2, and 3, nothing will happen because this condition will be failed for those nodes because those are already assigned to groups. We have finalized this part here by developing a reusable artifact which is now available for anybody interested in to solve a similar problem. The algorithm that we have implemented is linear in the number of nodes and number of edges, where n is the number of nodes of the graph and m is the number of edges. What we are going to tackle now is this upper part by solving our initial problem, but this time reusing what we have developed here. Let's pretend now that we are at the beginning of our journey to solve our initial problem, possible bipartition. We have already established the product use case and how it's going to solve the business case, and we have established a clear scope what needs to be included in our product. But we don't know what we need to search for, and that's the reason why we must invest some design work to understand that, hey, this problem is a graph problem. Is there any reusable asset which is providing us a way to partition a graph into two groups? In other words, solving a graph problem that can be mapped one-to-one to this one. And by formulating this search criteria very precisely, we would be able to find our graph service. Once we have identified this graph service, we need to investigate its API. It turns out that this graph service is solving exactly what we need here, although has a little bit of a different expectation. First of all, it accepts nodes labeled from 0 to n-1 instead of 1 to n, and it expects an adjacency list of a graph instead of just an array of edges. Now at this moment we can proceed in two different ways. First, we may perform all the necessary transformations outside of a service and simply just passing the service an input as it expects. The downside of this approach is that anytime another user would stumble across the same problem, then that user would need to repeat the same work. On the other hand, the benefits of this approach is that we don't need to touch the service. The second option is, and this is what we are going to do here, is to try to generalize this problem and put it back into a service in a generic form, in a sense that we would need to have another endpoint accepting the number of nodes n, the list of edges, and let the service itself do all the necessary work to convert this input into its internal format. There is one additional detail that we need to take into account, and that's related to this constraints section. Neglecting to include constraints into the consideration whether we can reuse something or not may have dire consequences on your users and, of course, on your enterprise. In our case, our service has an ON plus M asymptotic behavior both in runtime and memory complexity. It turns out that for 2000 nodes and maximum 10,000 edges, this is absolutely okay. Let me show you, for the sake of completeness, the transformation logic, what we have built into our service, represented through these two public constructors. This one is just an overloaded version of this one by passing 0 for the offset. Now, as you can see, it now accepts n, number of nodes, the list of edges, and the offset, which is this shift factor in the numbering of nodes. And in our case, when we would like to use this service for solving the bipartition problem, we would pass offset equal to 1. And all the rest here is really about Java-specific things and solving some legacy issues with generics. But all in all, at the end, you will have everything transformed into this adjacency list internal data structure. What have remained is known as plumbing work. So this is all what is needed. We would create an object of type graph, pass n and dislikes directly, specify one for offset, call bipartition, and test for null. That's all. In essence, we have followed the Volare requirements process, and the image here shows the flow of activities that are part of this methodology. I really encourage you to follow the link from this presentation and read more about Volare on the official website. The only thing what I would like to emphasize here is this part about requirements reuse. This means that we can not only reuse software artifacts, but we can do the same for requirements as well. The same vigilance and rigor that is needed for crafting a reusable software asset is imperative for requirements as well. Let me also show you SAFe5's requirements model. SAFe is an abbreviation for Scaled Agile Framework. You can see that this model is very sophisticated and full of details. Most of the time, companies are only focusing on this part here, but this is just one piece of the story. Both these guys on the left and especially this upper part with these non-functional requirements are quintessential for the success of large-scale projects. And let me show you or cite a documentation for SAFe, which best describes why there is a need for this really complex model. If the model appears complex, that's because contemporary software and systems development at scale is complicated even with agile methods. What can we conclude from this video? Without proper requirements engineering, agile projects usually enter a futile cycle of rapid customer, so to say, changes. But these changes are driven by dissatisfaction instead of enlightenment. And the reason most of the time for these cycles is ill-defined scope. Reuse must be planned and carefully realized. You cannot get reuse by chance. Requirements-related errors are the most expensive to fix and have far-reaching implications. And finally, the worst place to make shortcuts is in requirements engineering. Thank you very much for watching this video. I hope that you have enjoyed it. And if this is the case, then please click the subscribe button. Subscription on YouTube is free and you will not miss future episodes. Thank you again.